Over information.
Yes.
Okay.
Enthalpy of formation is defined as the formation of one mole of substance from the elements in the standard state. You know, all these things that you guys should know for the upcoming test. You know, well, how do you use enthalpy of formation? Somebody just tell me. You know, first you got to tell me what it is, enthalpy of formation, and then you use them. What's the number one use is to figure out delta H, some unknown delta H, right? Delta H of reaction. That's the number one use of it. And there we take the equation, the sum of the product minus the sum of the reactants. We did an example in class with the glucose using standard enthalpies of formation.
Okay.
And you should know how to do that. Okay, other questions? If you're careful, you know something tricky about enthalpies of formation that I warned you about. Or maybe you can look and see if you have that. Does anybody recall what was tricky that I said I might do on the test? I said that the standard enthalpies of formation are found where? This is just review. This is stuff you know. I've had many questions about you know how you know you want to do better on the next test from a number of students, and so you know one of the things I recommend is repetition, so that little things stick. But what was it that I said earlier about Appendix D in the standard enthalpies of formation? I wonder if anybody caught this. I said there could be something tricky on the next test with standard enthalpies. Since you asked me about standard enthalpies of formation, I'm just reviewing what we talked about regarding standard enthalpies of formation. And so I said something about the standard. One thing that might be tricky on the next test with standard enthalpies of formation would be that we talked about it when we were doing glucose. I said it about oxygen, mentioned about oxygen, O2 gas. Does anybody remember that? Appendix D said it's 0 kilojoules per mole, but I said, what? Well, what I said, let me just, no, spend too much time talking about this. What I said is that it's 0, but I'm not going to tell you it's 0. You should know that it's 0. The standard enthalpy of formation for O2 gas.
Isn't that the element itself?
Right. It doesn't require any energy to form O2 gas from O2 gas. And so that's the only thing that's tricky, because every time I do that, somebody comes up and says it's missing. The standard enthalpy of formation for O2 gas is missing. But I said, I send them back saying, well, you should know what it is, right? And then they go back to and then I see them that this didn't quite click, and they're struggling, and finally some of them just give up, don't answer the problem, right? But if that's the case, you're struggling, you don't know what it is, you can come up to me and I'll give you the value for small point deduction. You just don't want to leave a blank page. Okay? And so a lot of people do that. But you don't need a point deduction. You should know, because you know the definition of standard enthalpy. formation. Okay.
So isn't it for all diatomic?
No. That's something. Somebody tell me what it is for. You can make up a law. If you've seen enough observations, if you look, all you have to do is look at Appendix D, 0, 0, 0, 0, 0, and then you see a pattern. The pattern's so simple. What is the pattern? The pattern is all elements in their standard state have a standard enthalpy of formation of 0. That's it. Because you're going to form the 1 mole of element from 1 mole of element in the same state, and so it's not just for diatomic; it's for all of them. Okay. And so that was a tricky thing about standard enthalpies of formation. I don't know if it's tricky. Maybe it was too obvious in the register when I was asking. Other questions? No? All right. What did we calculate the lambda for the electron already? Yeah. What was it? Lambda for the electron was 0.242 picometers.
Or the 8.
Or angstrom, 0.242 angstroms?
24.2.
Angstroms, okay. Did I get this wrong? Picometers, 10 to the minus 12. So this would be what, 10 to the minus 13, 10 to the minus 14. I think there's a mistake here. So this was right at the end of class. And so what was the original number we calculated?
2.42 times 10 to the negative 11.
2.42 times 10 to the negative 11. I think the mistake we made was converting it to picometers and angstroms. So let me try that again. So if I want to convert this to 10 to the negative 10, so negative 11, 12, 13, so 10 to the negative 10 would be 0.242 angstroms. That's right. If I go to 10 to the negative 12, then, maybe that's right, 24.2 picometers. Is that what we just had?
I guess it was switched. Yeah,
Was it switched around? All right, it was switched around then. Because 10 to the minus 10, I'd have to move the decimal to this, making this smaller. The coefficient goes smaller, this can go bigger. 10 to the minus 12, I make the coefficient bigger. So this is at 24.2 picometers. What's the significance of angstroms and picometers? The size of atoms. And so the wavelength is about the size of the atom. You know, lambda is approximately the size of the atom. All right. What we have to look at is how the wavelength impacts behavior depending on the size of the object. So let's look at wavelength and size of object. So the first thing we're going to look at is a, let's say, a guitar string. I'm going to write it down here so I have room above. So let's say I have a string like this, guitar string, and I pluck it. if you plug the guitar string, it turns out, can I get any frequency I want? Any frequency, any wavelength of sound I want from a guitar string? Like, let's say I want a high-pitched sound. I can get a high-pitched sound from the same guitar string. Can I get a low-pitched sound? And any sound in between, high-pitch and low-pitch, from the same guitar string? Yeah. Then how come guitars have 6 to 12 strings? Why don't they just have one string if you can get any sound you want from it? It should just be one string, isn't it? Are all the, do you know, are all the 6 strings on a guitar the same? No. Some are, a little thinner and more tightly wound. Others are thicker and more loosely wound. It turns out I can't. There are only certain allowed, like for example, this string, let's say if I pluck it, this is an allowed wavelength frequency. In fact, this is 1/2 lambda, 1/2 wavelength. This is allowed. But let's say I wanted to go 1/4 lambda on a guitar string. I just want a little bit lower frequency sound, lower frequency, longer wavelength sound, let's say. So I go 1/4 lambda. Is 1/4 lambda allowed? No, I can't get it from this guitar string. I'd have to make a different string or make it longer or do something. If I made this longer, yes. But this is forbidden.
Professor Schiller said you wanted to get a lower frequency, longer wavelength.
Yeah.
And then why did you want to put that 1/4 to do that?
Well, I didn't have to do 1/4. I could have done something else. I could have done 1/3.
You just wanted to make the point that it's not within the...
Right. But because this one, there are only certain frequencies of sound allowed. What's the next one that's allowed? The next one that's allowed is, for this particular string, if I pluck it harder, I could get not one, but one full wavelength rather than 1/2 wavelength. Except I'm going to call this 2 times 1/2 lambda. This is allowed. But let's say I didn't want 2 half wavelengths. I wanted it 2.1 half wavelengths. Is that allowed, or that's forbidden? And so the next one that's going to be allowed is if I got to pluck it really hard. And if I plug it really hard, then I can get 3 half wavelengths in there. So 3 times 1/2 lambda. These are allowed. But it turns out anything else in between these are forbidden. And so we see that the energy of a guitar string is quantized. There are going to be allowed energies and forbidden energies. And there's going to be a distinct difference. Like this is kind of a big gap here, right? If we're thinking about this, in order to jump from this energy to this energy is significant, right? This is twice the frequency here. And so it is significant. All right, this is what happens when, well, actually, we can come up with a simple pattern for this. What is the pattern here? Do you see it? The allowed states are going to be n times 1/2 lambda, where n is equal to, yeah, 1, 2, 3, ... 2. It's a maximum. The maximum is going to be infinity here. And so what we see is there's an infinite number of allowed states. How many forbidden states are there? Yeah. And so here, infinite number of allowed states, but also an infinite number of forbidden states. Well, if there's an infinite number of allowed states, then why is this continuous? What would you say, continuous?
No.
No. And so infinite number of allowed, but also infinite number of forbidden. So eventually we just keep going up, you know. And eventually we'll reach a point where n equals this is the 1 billion. So here is my guitar string, and I'm going to get what? 1 billion half wavelengths. You know, this isn't even that big of a number, right? And so I get 1 billion half wavelengths. I can't draw it like that. And so is that allowed?
Yeah.
Yes, that's allowed. What's the next allowed energy? 1 billion and 1. Is there going to be a significant sound difference between 1 billion and 1 billion and 1? I mean, is it even going to be perceptible, do you think? In other words, is there going to be any difference? Let's say I need to pluck this. So I already plucked it to get 1 billion half wavelengths in there versus plugging it for 1 billion and 1. How much extra energy do I have to put in there just to get another half wavelength in there?
Very little.
Very little. And so this is what we see. We see when the wavelength is comparable to the size of the object, then the energy gaps are significant. Significant energy gap. However, when the wavelength is very small compared to the object, then are there big gaps in energy? You know, no.
Professor, how would you say a significant gap in energy? I understand in the guitar example, but I'm not really sure what you mean when you say significant gap in energy.
Significant gap in energy just means if you pluck it to get this sound, how much harder, how much more energy do you have to pluck to get this, what you call the overtone?
So it's like the difference between getting from one wavelength to another wavelength?
Yes, this is a big jump because here, boom, and then boom, and then you get this higher frequency, right? Versus this, you know, you're already plugging it very hard. Bang, and then you get this, but just to get one little half wavelength extra so that we're at the next allowed energy is 1 billion and 1 half wavelengths. 1 billion and 1 half wavelengths. Is that going to be a lot of energy to get that? It's already a lot of energy to get here, but is it going to be a lot more energy to get here? No. In fact, it's kind of a negligible gap. Right? This is a negligible gap. And so what does that mean for us? This is what it means for us. If I have an electron in this room, let's say, and it has this whole distance here, you know, how big is that wavelength? That wavelength is on the scale. That wavelength was actually smaller than an atom, right? And so how many half wavelengths would that electron have in going from this end of the room to this end of the room? Could you even count them? If the wavelength is about the size of an atom, you can't really count them because there's so many, right? And so let's say I'm pushing the electron across the room. I push the electron across the room. Can I push it just a little faster? In other words, add another half wavelength. Is it going to be difficult to put another half wavelength in the distance of this room?
No.
for the electron? No. In fact, the half wavelengths are so small, right? It'd be easy to add another half wavelength, another half wavelength, another half wavelength of energy for the electron. In other words, this is what we see. Electron energies in a room this size in free space are continuous. They're continuous because, you know, the half wavelengths are of no significance. We can take another big object. And so let's look at the tungsten light bulb. In the tungsten light bulb, we have a metal filament. You know, this gets hot. This is a hot piece of metal. Tungsten solid. And then we look at the wavelength of an electron in here. So let's say there's an electron confined to this tungsten filament here. And we look at the wavelength. The wavelength is very small, you know, compared to the object.
Compared to the filament or to the electron?
Compared to the filament. You know, if somebody were to ask you, you know, what is the size of an electron, what would you say? Well, you'd probably say electron is extremely small. You know, the atoms are what? Hundreds of picometers to angstroms in size. The nucleus is about 1/10,000th the size of an atom. And so electron's got to be smaller than the nucleus because the nucleus consists of protons and neutrons, right? And so electron has got to be small, right? And so how big is an electron?
And like tons of noise.
Maybe a millionth of the size of an atom? That sounds reasonable, right? And surely there must be something in the book that tells us the size of an electron, which is an obvious question. How big is an electron? There's a homework problem talking about the size of a proton. Do you remember that? Chapter 2. And so we know the size of the proton. And so the obvious question is, how big is an electron? What did the book say? How big? How big is an electron? What did Petrucci say? I didn't say anything, but you know, somebody will ask. Somebody can ask. 10 to the minus 16 meters?
Yeah.
10 to the minus 16. 10 to the minus 19 meters? 10 to the minus 19 meters? Okay. Where did you guys find that? In the book. But, you know, the size of an electron, that's something we want to know. But you double check your book's references because the size of an electron is not. Petrucci avoids the question about what is the size of an electron. He tells you what the mass of an electron is, 9.1 times 10 to the minus 28 kilograms, right? Something like that. But does he tell you the size, the dimensions? No, he doesn't tell you the dimensions because if you were to ask somebody what the size of an electron is, there's no size. Yeah, it's complicated. There's no size. The size of an electron is 0. That was the. So we'll talk about that later. But anyway, when I'm talking about the size of an object, I'm not talking about the electron. I'm talking about what the electron's in. And so the object here is the tungsten filament. And so the wavelength is much smaller than the tungsten filament. Well, if the wavelength is much smaller than the tungsten filament, then is there going to be a big gap between here? You know, how many half wavelengths is that? That's innumerable. You know, if you wanted to think about how many half wavelengths, and if the half wavelengths are extremely small, then to promote the electron from this, we need to add another half wavelength here. Is that going to cost a significant amount of energy or insignificant? Insignificant. And so what happens is this. Since the wavelength is so small, there's not a big energy gap, or there's not a big energy jump to the next level. And so what ends up happening is that an electron in tungsten behaves as if it were, the electron energy in tungsten behaves as if it were continuous rather than quantized. In fact, it is quantized, but the gaps here are negligible. And therefore, it is, for all purposes, continuous, and we get white light. In other words, we can excite that electron, and it emits pretty much all, in fact it does, it emits all frequencies of light. And this gap is so small. Does that make sense? So this is why a tungsten filament behaves like a, what do we call it? Things that emit white light. What do you call things that emit white light? A
So you're saying that because the tungsten filament is much longer than the wavelength of the electron, it ultimately can give us all of the whole spectrum of visible light?
Yeah, in other words, let's say this is, you know, a billion trillion half wavelengths here. The next allowed one is going to be a billion trillion and one. The difference in energy between having a billion trillion and a billion trillion and one is negligible. It's like this. If you're looking at temperature, let's say, do you think 5 degrees, let's say a 5-degree temperature change is pretty significant, isn't it, for us? So if it's 70 degrees Fahrenheit versus 75 degrees Fahrenheit, that is definitely noticeable, right? But what about this? Let's say we're a billion degrees Fahrenheit, and we just jumped from a billion degrees Fahrenheit to billion and 5 degrees Fahrenheit. Is that a significant change in temperature? No, not at all. That is a negligible change, and that's barely even a blip in terms of temperature, right? And so it depends on where we are, what perspective we have. And so this is like that. You know, the difference between a billion and 1 degrees is negligible, right? Whereas the difference between 0 and 1 degrees is significant. And so this is what I'm saying about lambda versus the scale. It's the same thing with temperature, depending on temperature versus the scale as well. You know, it has a different significance depending on what you're looking at. And so the same thing here. This is with tungsten filament. Now, if we did a tungsten atom lamp, how do you make a tungsten atom lamp? Well, tungsten atom lamp is you vaporize the tungsten atoms, right? And then excite the electrons. And so if we have a tungsten atom, the tungsten atom has electrons, correct? Are these electrons excitable? Yeah, we excite them. We excite the electrons. Are these tungsten atom electrons excitable to any energy we want? Like, for example, this is like the guitar string that can play any sound, you know. Are they excitable to any energy we want? No. Well, they aren't. Whereas over here, an electron in a tungsten filament is. You know, even though this is super, we have a lot of half wavelengths, it just takes a tiny bit of energy, a tiny, maybe just a radio wave or TV wave, you know, just to excite that electron from here to there. And Nothing very strong. Or if we had red, we could put in more half wavelengths in there. Or green, or blue. And so just anywhere this can absorb very little energy or lots of energy, right? It could absorb lots of energy, just pump in more half wavelengths in there. It's quite easily, and it's continuous. Eventually, it absorbs too much energy and the electron pops off. Whereas over here, we cannot electron. Now let's take a look. You know, here the size of the wavelength is comparable to the size of the object. Now the electron is not free. Here, this is like having a little fish in a big tank, right? You have a little fish in a big tank, then it's happy. It can move any speed it wants, right? But this is like you take a big fish and put it into a little tank. The big fish in the little tank is going to be constrained. And it's going to be constrained by this. Now you got a big fish, it's trying to swim. Can it swim at any? No, it's got to swim, and I didn't draw this just right. But here, I fit 3 half wavelengths in there. All right, what's the next allowed? Next allowed would be 4 half wavelengths. But, you know, this is confined. This electron's confined, but really it's 4 half wavelengths. Let's just go 3.5 wavelengths. That's what I want. I don't want to go 4. I'm going to go 3.5 wavelengths. So I'll try to fit in an extra half a wavelength in here. And what you see is this. If I try to fit in 3.5 wavelengths, eventually things become out of sync. And when things become out of sync, what happens is, let's say this. The blue line, this is 3 1/2 lambdas. Let's say the red line is 3.5 1/2 lambdas. Something like that. It's not perfect to scale, but you know, eventually it becomes out of sync. And when it becomes out of sync, we have this thing that happens with waves. With waves, you know, if you look, the positive amplitude of the wave here coincides with the negative amplitude. And so if I have positive and negative, what happens is they cancel each other out. And so what we end up with here is destructive interference of the waves. Whereas here, this results in constructive interference, that is. And so this is allowed, and this is forbidden. This is not allowed energy for the electron. And so the next allowed state for this electron is going to be 4. Now, think about this. The jump between 3 and 4, is that a negligible amount of energy or a significant amount of energy? It's a significant amount of energy, so there's going to be a big gap. The big gap means that we see quantization here. Quantization is going to be readily apparent in this case. Whereas over here, yes, there's quantization, but the gap is so small that it appears to be continuous. And so let's talk a little bit more. So you don't really notice these this quantization until you get to very small size, right? Because for big objects, you know, can we see a tungsten atom with our eyes? No, but can we see a tungsten filament with our eyes? Sure. For very large objects, you know, this quantization is minimal because the energies look pretty much, for the most part, continuous. And so let's do a big object, not an electron, but let's calculate lambda for a baseball. Let's say that the baseball weighs 145 grams and is traveling at a speed of, we'll go with a speed of 140 kilometers per hour. Okay, so if we want lambda of baseball, then this is matter, so we're going to use de Broglie, H over m times v. And so the mass we need in kilograms, so this will be 0.145 kilograms. And the speed we need in meters per second. And so let's change this from kilometers per hour to meters per second. What does that come out to? 38.9 meters per second. And so go ahead and plug these in up here. H again is 6.626 times 10 to the minus 34 joules times second. The joule is a kilogram meter squared per second squared. The unit should come out in terms of meters. So lambda for the baseball
times 10 to the negative 34.
1.18 times 10 to the negative 34 meters. Okay, thanks. When we look at the wavelength, we compare the wavelength. Now, what do we compare the wavelength? This is where it could get tricky, Asia, because before, when we were comparing it, we were comparing it to the object, that is, what the electron was confined in. But in this case, do we compare it to the baseball, or do we compare it to the baseball field? And so we're going to compare it to the baseball field. So let's say there's a person here and throws the ball to somebody over here, catcher. This is going to be throwing the ball, let's say, I don't know how many meters, let's say 10 meters here. 10 meters. So let's say this would be the object side. The object is the field. You know. So is this wavelength significant compared to the object? So in other words, 10 to the minus 34 meters, you know, how small is that? That's small. That's way, orders and orders and orders of magnitude smaller than an atom, right? Atoms are like 10 to the minus 10 meters. This is 10 to the minus 34 meters, which is 20 orders of magnitude smaller than an atom. Is that a significant wavelength? No. And so if we have, you know, if we have a wavelength that's way smaller than an atom, then let's say this leaves here at this point, and then I want this to hit here at this point. And so it's got to hit here, leave here. In order to do that, well, I need another, half wavelength in there. You know, is it going to be easy to do to put in another half wavelength? Or another half wavelength? Yeah. Here, the energy of the baseball is going to be continuous. Are there any forbidden speeds for that baseball that leave from here and hit this target? Are there any forbidden?
No.
No, it's any speed it wants to go is fine, right? Any speed it wants to go is fine. But let's say the baseball, if, hypothetically, if the baseball had a wavelength like this, if that was the wavelength of the baseball, then is any speed okay? No. The next allowed speed in order to hit here is going to have to be another half wavelength, which is going to be a big jump in energy. And so it depends on the wavelength proportion to the size, that is, the size of the object. The object is tricky because it's not the size of the electron I'm comparing it to, it's the size of what the electron's confined to. And so when we try to visualize what's happening with the electron, this baseball here, the baseball is continuous. Continuum of energy is allowed.
Are you thinking of the baseball as being confined to the field?
Yes, the baseball is confined to the field. Continuum of energy is allowed. The same thing, the electron, the wavelength of the electron is so small, if I confine the electron to a baseball field, can I push it at any speed it wants to go? Let's say I shoot the electron out at 60 kilometers a second. Any problem with that? Or what if I shoot it at, let's maybe shoot them slower. 60 meters a second. What if I wanted to go 60.1? Is that allowed or forbidden? Allowed. In fact, the difference between 60.0 and 60.1 meters per second is, pretty big, and so there are going to be a lot of half wavelengths in there. And so one way of visualizing what's happening with an electron in an atom is to do this, is to confine it like we did with the tungsten, or the analogy here is like this. The analogy is going to be an electron in a box. An electron in a box. So we confine the electron to a box, and we treat it like a standing wave, like a guitar string. And so we see, certain energies. And so this would be the lowest energy here, we call it n equals 1. And then the next one would be a big jump, n equals 2. But, as we go higher and higher here, eventually what's going to happen is we're going to get n equals 1,000,000. And then n equals 1,000,000,000. And in between 1,000,000 and 1,000,000,000, how many allowed states do I have? Well, 1,000,000 and 1,000,000,000 would be 10 to the third, 1,000, 1,000. So I have to draw 1,000 in between here. And eventually I'm going to get to n equals infinity. And so let's talk about this in terms of this. What happens is the gap gets compressed, and pretty soon, up here at these very high n levels, it pretty much looks continuous. It looks continuous because they're so close together, right? And the wavelength is so small compared to the size of the object in this case. Maybe object's not the best word for it, but that's one way to think of it. And so here we'll see significant jumps. Up here we see pretty much insignificant jumps.
Why is there 1,000 between 1,000,000 and 1,000,000,000? One, two, three, four, 5, 6. Way more than 1,000.
Oh, I don't know. Maybe I made a mistake. How many is there?
900.
So 10 to the 9. I shouldn't say, maybe I should have said difference between these two would be, okay, 1 times,
999 million.
yeah, all right. It would be 1,000, right, times 10 to the 6th minus 1 times 10 to the 6th. Is that right? So this would be 10 to the 9th. And so, yeah, what would that be? So that would be 1,000 times 10 to the 6th minus 1. And so you're right, it would be a lot more. It would be a lot. So basically, between these two would be not 1,000. It would be
990.
999 million lines. And so we apply this to the hydrogen atom here, and this is what we're going to do. We're going to plot out these here in terms of the energies. And so the first energy here is n equals 1. And then the next allowed energy, which there's going to be a big jump to, would be n equals 2. And then n equals 3. And then eventually we'll hit n equals infinity. Okay. And so between here and here, how many lines do we have to draw?
A lot.
A lot. And so what's going to happen is pretty soon these are just going to compress into pretty much, yeah, a continuum of lines. It's a huge number. So where do I get this, and how do I know? I mean, why isn't n equals infinity infinitely far up? You know, why do they compress like this? Well, let's see here. One is, you know, just fitting an extra half wavelength isn't going to change the energy that much. But another is, did I talk about the Heisenberg uncertainty principle? I mentioned it. And so we're talking about the de Broglie matter waves. The second part of this is the Heisenberg. And let's talk about that briefly before I go back to this. I think I went out of order here. But Heisenberg uncertainty principle just says this. For us, you know, for all matter, there is a limit to the precision that can be determined for energy and position. Use that simultaneously. Does that make sense? There's a limit to the precision that can be determined for energy and position simultaneously. What does that mean? Talk about that. You can know the energy and position. That is, we can pinpoint one, but the other will be uncertain. Or we can try to pinpoint both, but both will carry uncertainty. When I say pinpoint, pinpoint is just minimize. And so let's say the uncertainty in the position is delta x, and the uncertainty in the energy we'll call delta p, which would be for, do they use delta p? This is for momentum, which is the same as pretty much energy. So these are the uncertainties. This has to be greater than or equal to h over 4 pi. In other words, you know, if you pinpoint the position, that is, you minimize delta x, then delta p has to grow in response. Or if you pinpoint the energy, minimize the uncertainty in the energy, then delta x grows. Or if you try to do both, then you're going to have uncertainty in both. For us, what would we most like to know? For us, we want to know not the position necessarily, we want to know the energy. For us, we're going to pinpoint the energy. Therefore, the position is uncertain. It's not like a completely uncertain, you know. The position is going to have a probability. Now, it can't just be totally random. All right, this is different than Bohr. You know, in the Bohr model, what do you call? In the Bohr, he had orbits. And so let's say you determine there's an electron here, it's traveling this fast. You can pinpoint it like 1 second later, where will it be? You know, so if you know its path in the orbit, you know its energy, and you know its first position, you can tell where its next position will be at any time. And so this is deterministic, that is, we can determine where it will be at any point in time. What Heisenberg is saying, what Heisenberg is saying is he can't know exactly. If we know what the energy is, we don't know exactly where it's going, what the path is. And so this is not possible. This would be a violation of the Heisenberg uncertainty. And so if we combine these two, we'll take de Broglie Heisenberg plus the other development, that is the quantized energy in some basic physics. And combine all these things, we get the new theory of chemistry, and that is quantum mechanics. Quantum mechanics, at the heart of quantum mechanics is the Schrodinger equation. The Schrodinger equation pretty much just takes everything into account, and it's a simple looking equation. Looks like this. The symbol psi. But we don't have to worry about it. There's more to it. This just represents some mathematical formula. But what's interesting are these psi. This is the Greek letter psi. What the psi is equal to is the answer. Actually, there's not just one answer. There are many answers to the Schrodinger equation. And these answers have, they're called wave functions or orbitals. What the orbitals represent is they tell us all the information that we can determine for an electron. Contained. When I say all info about the electron is contained in there, certain things aren't, like how big an electron is. What is the color? What's the shape of an electron? You'd think the shape would be sphere, right? Or is it? And so this types, but what do we want to know about the electron? We'd like to know what the energy is and approximately what the position is. And so this is what the psi is going to tell us. We want to know what the allowed energies are. And so from the Schrodinger equation, we can apply it to the hydrogen atom. We get psi for the H atom.
What's psi?
Psi is
Is it this whole equation that equals all the info of the electron, or is it just specifically psi?
just specifically psi. The equation factors in all these kind of interactions here into it. And we get the psi. Psi is, the complete information about the electron. Complete as can be for this. And so we get this. This isn't that hard to solve for. All you need is some calculus, and you can solve for the orbitals of the wave functions for the hydrogen atom. In fact, in physics here, they make the students do this because of the calculus requirement. But I've done it, and everybody's done it once you hit a certain point. But for the hydrogen atom, how many psi's are there? How many allowed energies are there? For the hydrogen atom. I'll take a guess. Orbitals, yeah. But what are orbitals? Orbitals are pinpointed energy and probability in terms of position. All an orbital tells you what the energy of the electron is. The energy and something about its position. There's actually a little bit more in there that tells us things like angular momentum, how energy can be absorbed and emitted, those kinds of things. But those are finer details that we're going to omit. The two most important things an orbital tells us is the energy, number one, and a probability, or because it's in terms of probability, because it's not precisely known where that electron is. If it was precisely known, then we'd say it tells us the energy and the position of the electron at any time. But we don't. That's what the answers are. When we solve this for the hydrogen atom, what do we want to know? We want to know, what's that pattern of allowed energies for the electron in the hydrogen atom? How many allowed energies are there? How many allowed energies are there? For the electron in a hydrogen atom. We know that the electron in a hydrogen atom is quantized, right? Because it's stuck. An electron's stuck on the hydrogen atom. It's got the proton holding it there. If it were a free electrons are pretty much continuous. The energies, they're going to be continuous. An electron confined to a hydrogen atom is quantized. How many allowed energies are there for an electron in a hydrogen atom? Turns out that how many allowed? They're infinite. Infinite. And so if they're infinite, that means there's an infinite number of psis. If they're an infinite number of psis, that's crazy, because how are you going to calculate all of them? How are you going to calculate all of them? Well, it turns out you don't really calculate all of them, because psi, when you solve the Schrodinger equation, psi turns out to be another mathematical function. And you can solve them individually, it's not hard. Usually, like maybe in physics, they solve for the first 3 or 4 of them out of infinite, right? But here, the psis follow a simple mathematical pattern. The simple mathematical pattern comes from the math. When you do the math, you end up with 3 variables. Here, psi, n, l, and m. These are 3 variables that come from the math. And when you actually solve this and see, then it's very easy to see what the restrictions are, the patterns are. And so these are what are allowed, and everything else doesn't solve the Schrodinger equation. So for example, n, the allowed values of n are any value. The allowed values of n are n equals 1, 2, ... all the way to infinity. This is called the principal quantum number, this variable. Quantum number, or energy level. Energy level. So the lowest energy level would be 1, the highest energy level would be infinity. Those are allowed. And then the allowed values of L is called the angular momentum quantum number. And L takes on all values from 0, 1, ... to a max of n minus 1. M is called the magnetic quantum number. And M takes on all values from minus L to minus L plus 1, ... to 0, ... to L minus 1 to plus L. And so it just takes on all integer values from minus L to plus L. Going through 0. Each M set will depend on an L. So all values for a given L. So what these, actually, what time do I have? What these tell us, this pretty much tells us the energy here. L tells us the shape of the orbital and energy. Yes, sometimes the shape can change the energy, not always. M tells us the number and orientation of orbitals or size or wave functions. Number and orientation. And so let's build up the table. For the H atom, we usually do to represent the orbitals is one, we could have an energy level diagram where the energy increases like this. At the lowest energy here would be n equals 1. Okay, from the Schrodinger equation, that energy turns out to be minus 2.179 times 10 to the minus 18 joules. In fact, from the Schrodinger equation, we get the same equation that we had from the Bohr model. En is equal to minus r sub h over n squared. Same equation for energy as for different interpretation. Which is good because, you know, the quantum mechanics needs to not only explain the hydrogen atom, but also describe all the other atoms as well. Different interpretation and derivation. This was derived from the Schrodinger equation. And so the next allowed energy is here, the n equals 2. And then finally, up here, we're going to have n equals infinity. What's the energy at n equals infinity? This is E1 here. E infinity will be equal to zero joules. And so we go from minus 2.179 times 10 to the minus 18 joules to 0 joules. How many allowed energy states are there? How many allowed energy states are there? Infinite. And so I have to draw an infinite number of lines. Should I draw them evenly spaced? No, it turns out the biggest jumps are going to be down here, you know, when the waves. But as we get to higher and higher energies, you know, and shorter wavelengths, then the energy levels become more continuous. And so as we get higher and higher, these are going to compress. And so we need to fit an infinite number of these, and pretty soon it's just going to look like a continuum here. But down here, we're going to see significant energy gaps, right? It's going to look pretty quantized. So let's use some of the rules of quantum mechanics to figure out what these are. And so let's take a look at this n equals 1. When n equals 1, then what are my allowed L's? 0. Could I have L equals 1? Is that possible?
No.
No. That exceeds the math. So if L equals 0, then that restricts my M. I can go from plus 0 to minus 0 integer steps, so M is just going to equal 0. And so the first allowed state, we call this psi 1, 0, 0. And psi 100, how do we interpret this? Well, it turns out the psi 100 state we can graph as a wave function with this line corresponding to the nucleus. And if we look at it, it looks like this. This is our psi 100. It turns out that if we square the wave function, psi squared 100, then this is related to probability. And so squaring this is going, let's actually expand the scale since we're squaring this. And so I square this, I get something like this. That's my psi squared. And so normally when we think about the psi 100, we normally think about the shape of the probability distribution, like that. That's the probability distribution. And so if I put the nucleus here, what this says is that by the nucleus, I'm going to have the highest probability. As I get further and further away from the nucleus, this will be R. The farther I get from the nucleus, the lower the probability is. And so one way of visualizing what's happening with the probability is here, the electron might be here in one instant, and then the next instance here, here, here. There's no path, for the electron that we can map out, but we can just map out its position at different time intervals. And we'll see that it's going to have the highest probability near the nucleus, and that probability drops off as we get further and further away. We call this an electron cloud. An electron cloud tells us where it's likely to find the electron. And so when we look at the electron cloud, it's likely to find the electron close, but when we get farther away, the probability drops off. And we don't have a good chance of finding the electron. How big is the electron cloud? This is a trick question. How big is the electron cloud? Well, how big depends on the probability here. And so if we were to map out the probability, how long would this take to hit 0 probability? It turns out, yeah, it approaches it asymptotically, so it doesn't go to 0 probability until we're infinitely far from the nucleus. And so that means there's a minute probability that the electron might be very, very far away. But that probability is very small. And so if somebody asks you how big an orbital is, well, we can answer that. An orbital is going to be infinitely large. So does that mean that the hydrogen atom is infinitely large? No, because when we're looking at that probability way out there, it's so small. Now, typically what we'll do is we'll try to capture, instead of all the dots, we'll try to capture 90% of the dots here. And we'll call this a 90% boundary. Well, the 90% boundary is going to give you a better idea of the size. The size really isn't infinitely large. The size is more manageable if you consider the 90% boundary. Here, in terms of the probability. And so oftentimes we'll draw this as just the 90% boundary. So we'll just say psi 100. This is looking like this. That's what it looks like, a spherical orbital, like a ball. All right, this is a more common name. Rather than calling it psi 100, we call this the 1s orbital. The 1s orbital is the psi 100 wave function. So let's see.
We only always use 90%. That's our
Typical.
standard number.
Yeah. The standard for the other stuff is 95% confidence limit, but for orbitals it's 90% boundary. 90% boundaries will be used to draw the shape of an orbital, unless you use electron cloud. An electron cloud will be better. But is it a hard sphere, this is? No. This is approximation of the size of the orbital. So we can go to the next. That pretty much is it for n equals 1. And we don't have anything else that's allowed with n equals 1. When we go up to n equals 2, then we take all the L values starting with zeros. L equals 0 allowed. Yes. What's the next L? The next L would be L equals 1. Is L equals 1 allowed?
Yes.
Yes. For each L, we have to choose the M values. And so M is going to range from negative L to positive L. So M, in this case, is just 0. Over here, we pick the M values. And so it's going to go from negative L, which is negative 1, to positive L, which is positive 1, going through 0. And so this is the breakdown here. So the first orbital we get here is called the psi 2, 0, 0 orbital. And then the first one of these we're going to get is a psi 2, 1, negative 1, followed by a psi 2, 1, 0, and then a psi 2, 1, 1. We can do the same thing. We can take a look at the wave functions for this.
Psi 2, 1, negative 1?
Yeah. 2, 1, negative 1. If we look at the psi 2, 0, 0 wave function, it's kind of looks similar to what we just saw for the 1, 0, 0, except this. We call this here, call this positive amplitude here. This would be negative amplitude here. Whereas, you know, psi 1, 0, 0 just had all positive amplitude. This is why the probability has to be squared here, because you don't want negative probability. Have you ever heard of negative probability? No. And so what we're going to do is we're going to square this here. I'll talk about these orbitals next. This. The psi squared 2, 0, 0 is what we end up with. This point where it crosses the 0 line is a 0 probability. 0. This is called a node. You can see the node here, 0 probability. And so if we're to look at the electron cloud, there's a nucleus in the center of this. And the electron cloud would look like this. The greatest probability is very close to the nucleus here. So we're going to see most of the dots near the nucleus. But that probability is going to drop rapidly to, got this, and then the probability drops to 0. So this is going to be the node here. Node. And then after the node, we'll see an increase in probability, which is going to decrease eventually down to 0. And so it becomes less and less probable as we get further and further away. And so a node is a region where we're going to have zero probability of finding the electron. And so when we're thinking about this, you know, if there's zero probability of finding the electron here, then how does the electron go from here to here without going through this blue node? Well, if we think in terms of an electron being a wave, then yeah, waves we can have a node, you know, in a wave. For example, here. A node here. And then we have some, you know, positive amplitude and some negative amplitude. Well, this was the positive amplitude portion. This is the negative amplitude portion. So you can think of it like that. And so for waves, it isn't unusual to think about that. For particles, it'd be unusual to think about that. All right, so that's this, and this, if we did the 90% probability boundary, it would just look like this. It'd just be a bigger sphere than the 1s. So this is called the 2s orbital. The 2s orbital, it's a higher energy electron. N equals 2, so higher energy, that means the electron can be further out beneath this. The energy is given by the Schrodinger equation. We know what the energy is. The energy turns out to just be E sub n equals minus r sub h over n squared. So this is just 1/4 minus r sub h. That's the energy of this. You can calculate it easily. The next orbital we're looking at is the psi 2, 1, negative 1. We're going to have a series of these orbitals. We're going to have the 2, 1, negative 1, psi 2, 1, 0, and the psi 2, 1, 1. If we look at these, you know, the shape of these in terms of the wave function, psi versus r here, it's going to look like this, where there's going to be a node right there. And so here we have positive amplitude, here we have negative amplitude. But, you know, we got to look in terms of an x, y, z coordinate system. And so we could have a wave like this in one orientation, or we could, you know, flip this like this in another, and then have a wave like this. So depending on how we label these, you know, we call these, well, actually, we do the psi squared. Psi squared. We do the psi squared, it's going to look like this. Okay, where this was originally positive, and it's still positive, but this one that was negative, when you square it, you're going to lose that sign, right? And so what we do is we carry that phase information. This is called phase information. The phase information is lost when we square it. So the way we do it to keep track of the phase is just to write the sign of the wave in there. And so the sign or the phase is written in. Anyway, and the reason it's written in is because this was the negative. This is like, you know, what I'm talking about here is the square root of 2. Is the square root of 2, or actually I shouldn't use 2. magnitude. Let's do square root of 4. Is the square root of 4, is that plus or is it minus 2? Do we know?
You don't know.
We don't know. And so this is called the phase. And so to make sure we don't lose track of it, we just carry it down, the phase information. We carry this down so that we know what it is. Why do we care? Because the phase of the wave plays an important part in forming bonds. And so we need to know what the phase of the wave is when we make a bond. Okay, I'm going to stop here.